Hello, everybody. Yes, the challenge today will be to stay within 50-55 minutes, as Marietta said. The presentation will be driven by the three main questions that you have in front of you right now. One, which is associated about the performance of a multi-phase flow meter and how to make it, to do. Second one will be associated with the fact how do we test such meter and the performance of this meter. And the final one, which I believe is the most important one, it's associated with checking the performance in field condition. So Marietta said, I will introduce myself. So I'm in this business of multi-phase for the last 30 years, and I had two lives in my life. I can say two professional life. 26 years with one company, and 4 years with Nail right now. So before going further, obviously everything that will be said today, and if there is some mistake, it's my fault. It's definitely not something related with TÜV SÜD. It happens that I'm doing mistake. Before going further, I was using the word measurement or measuring, and I will use it a lot in this presentation. And I want you to understand, this is a quote coming from James Harrington, and I highlight in blue what I believe is quite important, If we don't do a measurement and if we don't do a proper measurement, there is no way that we can understand what we are doing. And on a worst case, we cannot even control it or even improve. And, you can put whatever you want around that. For me, I will say control the production and improve the production and understanding your reservoir management, So this is fundamental. You need to have a proper measurement, and this is all the idea of this presentation here. So I have three main topics. One, driven with a manufacturer, or what the manufacturer should do, in order to establish the performance of multi-phase flow meter or white gas flow meter. Very often I will use multi-phase flow meter. In my presentation, you will see sometimes MFM, but it's either one or the other, The bullet number 3 will be for the end user, and after we look at the verification in the field and then a conclusion. So let's go through the first part and an introduction. And the first question that you may have is, why do we need to test a multi-phase flow meter? It could be well established like a Coriolis or some other equipment. Unfortunately, and this is what I said at the beginning, it's the multi-phase flow meters are small equipment in general, they compete against a separator and they need to be more compact than a separator. And inside this small place or space, you have a lot of technology, different type, could be electromagnetics, could be nuclear, could be electrical, could be optical, and all these things are combined together, and it's far too easy to understand entirely the system and how it can deviate or establishing a proper propagation of error. So you will need to do a test in a way or another. Convinced or not convinced by what I said, you can take it in a different way. For example, a Venturi, there is an ISO associated with a Venturi, but the ISO, 5167, as mentioned here, it's related to one phase and not 2 or 3 phases like you will have in multi-phase. Same story with the Coriolis. The Coriolis has been developed for 1 phase. They have been tested and they try to improve it for 2 phases, but in some cases, you may imagine we will have 3 phases here and we need to be able, or some people will try to make this Coriolis working for 3 phases. So sometimes it's not new technology combined together. It's a very well-known technology, but extended beyond this normal condition. On the top of that, to complexify a bit the problem, the fluid mechanics, for some of you, I'm sure you're good in this domain, it's far too easy to understand, and all the equations that you will have are non-linear equations, so you will need to do some assumption in order to be able to solve them in this system, Obviously, you can imagine that all these things leads to one statement that I said earlier, it's the best way to look at if this equipment is working is to test, to verify the claims or to establish the claims for a manufacturer. So specification of a multi-phase flow meter will be established by having some range of gas volume fraction, GVF, we may see it again in my slide in the future, and water liquid ratio, WLR, you know. So following the range of these two parameters, they will be able to establish a performance, let's say, between 20 and 30% GVF and between 50 and 100% WLR. The specification on the oil flow rate could be 5% or something like that. Unfortunately, what I was telling you, it's far to be right. Most of the manufacturers today on the market are not giving the specification like the end user expected. The end user wants what? The oil flow rate, the water flow rate, and the gas flow rate. This is what is used with a separator, and this is how the allocation is done. Unfortunately, for some reason that we will not discuss here, manufacturers are giving a combination of parameters, and the end user will need to establish the proper statement in terms of oil, gas, and water flow rate. I show you some type of specification. You know, I'm listing here 4 of them, which are quite well known, you know, among all the manufacturers on the market today. Little, you know, as I said, there is only 2 as far as I can see, which are providing the gas, the water, and the oil flow rate as expected. You know, I call them type 1 specification. The type 2, which is a larger one, it's based on gas flow rate, liquid flow rate, and water liquid ratio. Okay. The type 3 is gas flow rate, a mass of hydrocarbon. We need to be careful here. We're talking about a mass, and we have the water volume fraction, and we have the type 4, and we have the type 5. I show you here how you need to do the calculation if you want to get access to the oil flow rate, gas flow rate, and water flow rate if you were with a type 4, for example. So you see, you will need to get access to the density of oil, you will need to get access to the density of gas, and manipulating the specification given by a manufacturer, you will be able to access to the statement that you want. So how work a multi-phase flow meter? All these multi-phase flow meters, even if they are complex to understand, they are based on the same concept. You will need to have some information to set the meter. Could be the salinity, the density of oil, the density of the water, the density of gas, and obviously the pressure and the temperature in order to be able to do the conversion from standard condition or ambient condition to line condition. And then you will have some other information. Very often you will have the differential pressure measurement. Most of the manufacturers on the market today use a Venturi in one way or another. Some may use a Coriolis. In this case, it's slightly different, but this is all the input parameters that you will have. So this is what we have on this side, on the left side of this slide. And, you know, we need to achieve these things for the end user, which is a flow rate at standard condition. And how do you go from the left to the bottom right? It will be obviously by combining the information that you have, okay, converting them at line condition. So this is a bit of data processing. You will need, and each manufacturer will have his own model for the fluid mechanics. You need to use some equation of state or phase behavior, like I said here, and then you will be able, by crunching these things, getting access to the flow rates at line condition. Mass flow rates, liquid, gas, and so on. It depends after all the technology that you have, you know, and how they combine them. And then there is an averaging to do, obviously, because this data acquisition frequency will be quite high, you know, to be able to handle the type of fluid which is passing inside your pipe, you know, and which are quite often unstable flow. And you do this averaging, and then you will use an equation of state again to do the conversion to standard conditions. So this is what you need to have in your mind when we are talking about a multi-phase flow meter or a wet gas flow meter. So the things now will be to establish the first things that, and the manufacturer, what they want to do will be to establish the uncertainty of this equipment. So how do we establish the uncertainty of an equipment? The first thing is we need to understand that an uncertainty should be based on 2 variables. I'm taking here the gas flow rate, it will be based on an error on a percentage of the reading. So let's imagine here I have been calculating and reading X, which is a value of gas flow rate, I will multiply it by this specification or this uncertainty in percentage, and this will give me a number, or it will be an absolute value. It will be always one or the other. The differential pressure measurement is based on the same techniques. So I give you an example here. For example, in this case, let's imagine we have a relative error of 3%, which is a statement made by a manufacturer, and we have a cutoff at 5 cubic meters per hour, and the gas flow rate will be the max of one or the other. Very, very often, when I'm auditing equipment, I see that this one is missing here. There is always a suspicion when I see these things. It means for me that this equipment has not been tested on the full range that probably it's claimed by this manufacturer. There will be always a cutoff somewhere, especially when you go to the low value, in this case of gas flow rate. You cannot maintain an uncertainty of 3% on the full range, and you need to have this kind of cutoff. This is what I'm saying with these last bullet points on this slide, where I say, let's imagine that I have a flow rate between 0.01 cubic meters per hour and 1,000 cubic meters per hour. And if someone is claiming 0.1% accuracy or uncertainty is the right word here, it means that he is capable to have an uncertainty of this value for one case and this value in the other case. And you can see that these numbers are way too different, and this will never happen. Okay. So keep in mind, when you develop a specification, you should have a cutoff, and essentially this cutoff is for low flow rate. Now, we have established how we should write this specification or this uncertainty, and what are the ingredients that we'll need to use, to establish this uncertainty. And there is few of them, and the main one, the 8 of them, as I mentioned here, are here. You need to take into account the repeatability of your equipment, and we will see a bit later why it's so important to have information about the uncertainty associated with the repeatability. We have the reproducibility. We have a stability, and this is something that you build over the time. You may have a bias. Obviously, if you develop correctly the system, the bias will be zero. There will be a drift that will happen, in your system over time, and there is also a way to handle it. There is a resolution on the equipment that you are using. Very often today, the resolution is extremely good, so this number will be close to zero most of the time. And you will need to take into account the uncertainty and the stability of the equipment that you are using to establish the uncertainty on your multi-phase flow meter or wide gas flow meter. Usually, this number here will be also extremely small and will not affect drastically the overall uncertainty on your equipment. However, this value here will not be small when we are in the field, and we need to keep this in mind when we will reach the end of this presentation. So this is the first things. Now, there is also some statement in order to do a comparison between the different multi-phase flow meters, okay, and establish how good one is against the other, all the uncertainty should be given with a 95% confidence level. So what is the meaning of 95% confidence level? It's in fact an expanded uncertainty, based on standard deviation. So when you are collecting data, you will be establishing the standard deviation on these points, and then you will multiply it by a K factor, coverage factor, and this coverage factor will give you a statement at 95%. I mentioned this 95% because I still see time to time some specification given not with 95 but with 90%. If it's not 95%, you will need to do some correction. There is a way to do it, obviously, in order to be able to compare apple to apple. Okay. So what we will get at the end, taking into account the right type of distribution, is it normal distribution, rectangular or triangular? There is different way to use them, but in our case, when we are establishing the gas flow rate or the oil flow rate and water flow rate at the end, the K factor here will be associated with a normal distribution, or we'll see a Z distribution, a T distribution, and this K factor here will be something around 2. I will give you exactly the number just after. Okay, so it is the statement that we have done, and we multiply it by this K factor. So it is obviously associated with some statistic, okay, and statistic means that we need to collect number of points, and all the question is how many data points should we collect in order to get a proper K factor, or as small as possible this K factor here. So this is all the idea now, you know, in the development of a specification. So I'm presenting here what most of you will know, you know, the normal distribution, the bell curve or bell-shaped curve, or the Z distribution for some of you. Essentially, the system is saying that if you want to have 95% confidence interval, you will need to multiply the standard deviation by 1.96. It is not 2, it's 1.96. If it was 99, it will be 2.58. I mentioned it clearly. The value or the coverage factor that you should be using with a normal distribution. But to use a normal distribution, you need to have a large number of points. Very often when you are doing tests on a facility, due to the price, due to the fact that you don't have maybe a lot of time, you are collecting not 100 or 200 data points. You will be recording far less data. And in this case, it's not the normal distribution that you will need to use. It is what we call the T distribution, or for some of you, you may know the student distribution. I'm showing you here, I copied it from the web, you know, what's happening if you have 3 data, 4 data, 5 data, 6 data, 11 data, 21 data. I'm not drunk, you know. Here, this number is referring to the degree of freedom, and the degree of freedom is the number of data minus 1. So this is why you can see I'm giving you the number of data and not the degree of freedom as presented here. What is very interesting to look at is if you have a little amount of data, you see this dash curve in blue highlighted here, you know, and I'm presenting it with a laser pointer right now. This is the curve that you will have. And if you had a normal distribution, this blue one will be this curve. And you can see both these two curves, you know, are not exactly fitting on the top of each other. You can see that the tail of each of them, you know, one is much higher than the other one, and this is obviously the T distribution here against the Z distribution. So therefore, the K factor for T distribution will be larger than a Z distribution. And all the idea is how large is this number, and this number, it depends of the degree of freedom that you will have in your system. Okay? So, for example, imagine that you collect only 8 data points. You are very fast, you know, and you want to get only 8 data points. The K factor that you will need to use is not 1.960, but it will be 2.306. Okay? If you collect more data, you're a bit more patient, and let's double the number. You will go for 2.12, okay, or 120 if you want. And if you increase it again, you know, and let's say you go to 40, in this case, you are 2.02, and you can see that you are converging step by step to the famous 1.960, okay? So keep this in mind. When you are going to a facility, you do some tests at a given range of WLR and a given range of GVF. If you have only 20 data, the coverage factor that you will be using, it will be 2.086, and this will be reinforced in the near future by the different standard coming out, you know, either the API or the ISO standard. Okay, and please keep in mind if for a reason or another you have a lot of data, it's 1.86, it's not 2 that you should use. You know, I have seen so many people using 2. I don't understand why people want to get an uncertainty 2% off. You know, it's already difficult to get a small number, so use the right number when it's required. So we have been able to establish the coverage factor. We know how to describe the uncertainty. How do we do now to validate this multi-phase Flowrate? We will need to work in a different range of GVF. you should collect some data in a low range of the GVF, in a medium range of the GVF, and a large range of the GVF, except if you want to sell a wet gas flow meter. In this case, you will be only in a large and very large and even higher, in terms of gas volume fraction. But in general, this is what you need to do. In WLR, water liquid ratio, you need to address the low range, when you have a little amount of water, and you need to also address the case when you have a large amount of water inside your liquid. So you need to have the full range. And in terms of flow rates, you should not stay in a sweet spot in the middle of the range of your meter, but you need to have some data in a lower range, some in a medium, as I said, or the middle, and some in an upper range. If you don't do that, when the end user will be using your meter and verifying if it works, you may be surprised that suddenly you don't pass this test. After you have been collecting this data, I have seen some strange things happening time to time. People try to remove some points, because they believe that this point is wrong, There is only one way to look at if these points are wrong, is to use outlier corrections. There is plenty existing on the market. Techniques, I'm saying, I'm gas with a Dixon's test, but you can have some others. There is Rock, there is Mundell, and so on, These techniques will tell you if a point is outside of the distribution, okay? And in this case, you will be able to spot it, but you should not remove it just like that. You will need to understand what is the problem associated with this point. Did the flow was unstable and you were expecting to have a technology working only with stable flow? Is it a time shift that between the reference and the multi-phase flow meter? They may have an explanation. Without any explanation, you should not be removing these points. Okay, and this is the only way to do it. You may have a bias in some cases. If you have a bias, it's a systematic error that you have in the system, and then this is something that you can be able to correct in order to establish the performance of your meter. You should avoid to have a bias in your statement, definitely. Now, how do we do? And I'm presenting here in the table, the typical table, that you have for multi-phase flow meter. You will have a range of gas volume fraction. Here I'm presenting 4 range. I don't put any value here. The X, Y, Z will be something that will be defined following the technology, and you will have the WLR here, and again, here I present 4 cases. So if you have 4 here and 4 there, you will have 16 boxes, and obviously you will have a statement for the relative error in percentage and for the cutoff in absolute error. So you will go now from 16 to 32. In some cases, you will see this number are meaningless and you can remove it. But this is a way to establish the uncertainty associated with a multi-phase flow meter. And now the trick, it's if you want to establish the performance in this area here, for example, in yellow, you want it at 95% confidence level. So you will need to know how many data you have been recording in this specific range, okay? And if it's only 8, you know that the coefficient was 2.12 or something like that. We have seen it just before, and it's not 1.96. So you need to collect in this domain here enough data to be able to have a coverage factor as close as possible of 2 or 1.96. So if you have a large description in terms of range of GVF and WLR, you need to collect a lot of data to be able to establish a proper uncertainty and performance for your multi-phase flow meter. Obviously, someone which is capable to state a statement versus gas volume fraction, for example, and whatever the WLR between 0 and 100% will need to collect less data. In this case, you have only 4 options, and you will need to collect enough data in each area, and you can have a better statistic. Probably will be slightly larger than this one here, where you have a lot of split, but this is a way, I can say, to improve the statement or the value of the K factor. Okay, this is up to each manufacturer. Having described getting access to the information about the performance, we have now in our hand the expanded uncertainty. Expanded uncertainty is a k-factor multiplied by the standard deviation. But this, you know, when I put it in red here, this doesn't reflect the entire performance or dependency that you will have in terms of performance for this multi-phase flow meter. And if you start to look at the ISO and API and the new one that will be coming out, you know, they want to get access to the repeatability, the reproducibility, the drift, but also, it is mentioned, the sensitivity that this system will have to some change. Could be a presence of solid, unfortunately, time to time, or salinity change, or probably chemical, you know, to avoid hydrates or wax deposition and so on. So you need also to establish what is the uncertainty or the sensitivity that you will have to these parameters. Okay, and don't be surprised if you see over the next years, you know, these things coming more and more in demand, you know, for the manufacturers. This will be the way to establish properly the performance. I talk a lot about the repeatability and reproducibility, and I wanted to tell you how we calculate the repeatability of an equipment. So it's, you will say it's quite easy. You take one day, you know, and you collect some points at different, at the same condition, you know, and you do it at different times, you know, and then you use the standard deviation, and then you use this equation here, and you get access to your repeatability. This obviously it's a way to do it. The repeatability should not be confused with reproducibility. So it means you do a repeatability by switching off your meter, touching nothing, switching on again your meter, and looking at the performance. And you can do it a few times. Here, for example, I have 5 dots, so it means that in this case we have been doing 5 times. And then higher is this number, and better will be your statistic, because the number n is coming up here. The reproducibility is slightly different. It's you record in a condition 1, for example, on the day number 2 here, and you do it on the same condition on the day number 3 and 4 and 5, and then you have now 4 points, which are reproducibility of one against the other, you know, and then you can start to establish the reproducibility for this one, and you do it for all of them. And at the end of the day, it's exactly the same type of equation that you have. The way to calculate it is slightly different, but you obtain the same value here. So we have access to the repeatability, we have access to the reproducibility, and we will need to see why it's so important. It's important to establish the performance, but it's also important from the end user point of view. We have been spending almost half an hour together right now, you know, 25 minutes, and I wanted just to make a break, you know, and you may remember what Donald Rumsfeld was saying, you know, in 2002, you know, we have some unknowns, you know, and we may know some unknowns, or there are things that we know and we don't know, and this is what we want to try to address in this section. So first thing that needs to be clear, and now we are not anymore with a mindset of a manufacturer, we are with a mindset of the end user. Very often the end user, before buying or when he is buying this multi-phase flow meter or WGFMS flow meter, he wants to do a test. And he needs to understand, I put it in red, you know, he needs to understand that the purpose of this test is not to establish the performance of the flow meter. Not at all these things. It's to check if the multi-phase flow meters is within the given specification that the manufacturer has been providing. Okay? And it's nothing else than that. It should not be too complex, if I can say that, you know, and we will need to look at how we can handle these things. Obviously, it will be important to do it, as I said, in a low range of the meter, in a medium range of the meter, and an upper range of this meter, as described earlier. What do we have? A statement on the performance. Let's say my meter is plus minus 5%. It doesn't say that all the data will be for within 5%. It says that there is a probability, and this is associated with the 95% or the confidence level that we have described. There is a probability that it will be within this 5% for 95% of the time. So time to time it can be out, but when it is out, doesn't mean it's wrong. You need to look at from a statistical point of view how often it's out, and if it's too much out, obviously the claim in terms of specification from the manufacturer are wrong or is not fit for the application that you have. Okay. So back to what I said earlier, we want, from an end user point of view now, we want to look at not the mass flow rate of the oil or the hydrocarbon, we want to look at the performance associated with the oil flow rate, the water flow rate, okay, and the gas flow rate, obviously. So the first things, if you are not in a type 1, but you are type 2, type 3, or type 4, you will need to do, someone will need to help you, to do the calculation of the flow rates and the uncertainty associated with this flow rate, okay? I'm giving you here, in a generic manner, how the gas flow rate is depending on some parameters, the oil flow rate and the water flow rate, following if it's a type 1, type 2 specification, or 3 or 4, And I'm highlighting here, we are not going, in this hour through the full description, but let's imagine if I have a specification which is associated with the gas flow rate, the liquid flow rate, and the WLR. I will have obviously the gas flow rate uncertainty immediately. This is provided by the specification of the manufacturer. But to get access to the oil flow rate, I will need to use the uncertainty from the WLR and the uncertainty from the liquid and calculate what is the oil flow rate and what is the water flow rate and what is the uncertainty associated with the oil and water flow rate. And this is what I want to highlight here. Okay. If you have a type 4, okay, you can start to see that it's a bit more complex, it's in orange here, and you can see that you need 2 parameters for the volumetric gas flow rate uncertainty, and you will need to use 4 for the oil flow rate and 5 for the water flow rate, okay, and the uncertainty associated with that. So the equation can become quickly large. We use a technique, which is generic, whatever the type of specification that you have. And, I remind you here, what are the type of specifications that we are talking following the claim, or the statement from the manufacturers. And I'm giving you here the way the calculation will be done, okay? So obviously, the purpose is not to spend time to explain you these things, but there is a technique to do the calculation. And we use, in our case, a table concept. There is different type of table concept. We introduce here the different parameters that you have, the value associated with these parameters. So sometimes it's 0 because, you don't use some of these parameters. For example, if I was with WLR, liquid, and gas, I will have only 3 lines here that will be used. All the other will be at 0. And then we take the uncertainty given by the manufacturer, we will calculate the absolute error for the given value. Then we are using the probability here, it will be the normal distribution, so the divisor will be 1.96. We calculate the standard deviation for this statement. Remember, if you were with a manufacturer which is not giving you 95% but 90%, the coefficient here will be slightly different. And the division here will be obviously different. You need to calculate the sensitivity factor. This is what it takes a bit of time, to establish. And then you multiply this column by this one, you get your uncorrelated product. If you have done a proper work, there is no correlated product in your system, and then you can calculate the variance. Adding the variance, you do the sum of your variance, and then you take the square root, okay? And you need to establish at 95% it goes this way, So you have the square root, you will divide the square root by 1, so you get this number here. And then you will need to establish the normal distribution at 95%, so you will need to multiply by 1.96. Oops. And then this is what you are obtaining here. You will get your uncertainty at the absolute one and the relative one for the given value that you have. In this case, I took an example with oil volume at line condition. So based on the statement from the manufacturer, you are capable to establish the uncertainty associated with the oil. Here, you will have the same thing with the water and the same thing with the gas. Obviously, we have been taking into account only the specification for the moment. We need now to take into account the repeatability, the reproducibility, the resolution, the drift that you have on this equipment. None of the equipment, is always working perfectly for the next 10 years, Very often the manufacturers are saying that they need to see the meter on a yearly basis. And one of the reasons could be that they want to look at the drift. You need to look at the stability and the gas. I give you here a type of calculation that we are doing, I imagine that it was 1 quarter ago that we have this calibration of this meter, and therefore the value here should not be 0.1, but it will be a quarter of 0.1, so which is this value. And then you do the calculation, and what do you get at the end? This value here, I said earlier, are very small, and they should be close to 0 if you are going to the right third-party facilities when you do the statement of the performance of your meter, okay? And you can see that from a 3% uncertainty that we have at the beginning, we come to a value which is slightly higher, 3.12. You may think, you may say, well, it's not so much different. It's 4%. If you are in a location, and if this meter was used, for example, for custody transfer or fiscal allocation, obviously there is a difference here that you need to take into account. We have been able to establish the uncertainty from the end user point of view. Now we need to establish the criteria that the meter should face, in order to state if he pass or fail. I say it again, several times here. The value of the meter is, or the uncertainty of the meter is given with a confidence level of 95%. So in red, I say it will not be 100% inside the specification. So it's not because you record 12 points and there is one out that the meter is out. No, it's not that way. You need to look at how the system behaves. What do we have in our system? We have either it's inside the specification or it is outside. We have a probability. The probability is given, it's 95%. And you may remember from your school, in this case, when you have such concept, you will need to use a binomial law or some analysis associated with a binomial probability. And I give you here the formula that needs to be applied, where N is representing the number of tests and M is representing the success. So you are within the specification given by the manufacturer, or you have been calculating yourself. And then you need to establish the failure criteria. So this is quite simple. I give you here, for example, for 2 tests, 3 tests, 4 tests, 20 tests, 21, 30 tests, what is the maximum failure that you can accept before to say that the meter failed to pass this test. So let's imagine you have been recording 20 points, okay? You should not have more than 2 points outside the specification in order to declare that this meter is good for your application or pass the test, okay? So this is what is important to remember. You are not going to state if the meter is with or rewriting the specification of the manufacturer. This has been done by the manufacturer at a given time. You are, as an end user on the facility, looking if the meter is within the specification given by the manufacturer with this uncertainty and the confidence level associated with this uncertainty. Okay? And this is the way to do it. Now, and this is the last step. Very often, you buy the meter and you want to check how this meter is performing when you are in a field condition, or you want to verify it, or probably the person in charge of the operation, is not comfortable with this system and doesn't believe that suddenly there is so much water coming out of this well, and then the comparison will be necessary. So I'm trying here to give you some, before we look at the formula that you should apply, we need to look at what you should do in a field condition. Now we're in a field condition, okay, and this is the end user. Probably the end user will ask the manufacturer to be around, but he can do this test without him for sure. I'm highlighting in color, what is repeatability, what is reproducibility, and what will be accuracy, or high accuracy or low uncertainty on your measurement. Okay, and I'm showing you the main type of application where I have seen multi-phase flow meter and weight gas flow meter used. Obviously the main one is well allocation. You have a multi-phase flow meter installed on each well, and you look at the production from this well. And I'm highlighting in green what is associated with repeatability, and in orange with reproducibility. So if you are in a well allocation, and we will see after with the graph on the side, essentially what you want repeatability and reproducibility. Why? Very often you are using a K factor, in order, or another allocation factor, you will call it, in order to do a perequation or weighing the flow rate that is given from this well. So for example, this well may be producing 100 barrels per day, but at the end of the month, when the allocation is done, they say, no, it was not 100, it was 90%, 90 barrels per day, so you are 10% below because the allocation factor is 10%. So essentially what we will be looking here, obviously, if we have a high accuracy is good, but the main things will be repeatability, reproducibility. If you are in a partner allocation, so partner allocation, you are in the same field, you have an agreement between two oil companies, it's the same thing that you want to look at. If you are in a custody transfer, so you transfer your production of oil and you expect some dollars, obviously you want to have the repeatability and reproducibility, but you need to have access to the accuracy. And if you are in a fiscal allocation, very seldom we use multi-phase flow meter, but if you are in this area, obviously it becomes very, very important to have a high accuracy. So how do we do repeatability in a field? Here I'm presenting, and I want to thank people who give me access to this data. You have the time, whatever here, we have a liquid flow rate, and what was happening is we get it's a comparison between a multi-phase flow meter and a separator in this case. Okay, and the first things to do is we do a recording with a multi-phase flow meter, is a light blue, and then after we are stopping this meter and restarting the meter, we don't change anything, and we look at this value against this one and do they fit to each other, and we do it a few times during the test. The reproducibility is what I said a bit earlier. We are in one condition. We will change this condition. You can see the flow rate increase. In fact, we were increasing the pump, but you could have changed the choke, for example, or the gas lift value, all these kind of things. Here has been changed to a higher value and lower value. You can change only once. Here it was changed twice. And then it came back to the same statement, and we are comparing this data here against this one. This is reproducibility. This is what is very important for you. You may open the choke, you may close the choke, and when you are back, you expect to read the same thing. If you don't read the same thing, in this case, you are lost, in terms of measurement, and you cannot improve or optimize your production. And then, obviously, after you look at for each recording, you need to look at what is the difference that you have or the accuracy that you have between the data that you're collecting with a separator and the data that you are collecting with a multi-phase flow meter. So these are really the things which you need to have in your mind as soon as you want to do a comparison. Before looking even the data, okay, you need to look at this repeatability and reproducibility. Now, to do this in-situ verification in a field, there is few statements that you need to have, okay, which were applied in the data that I've been presenting just before. First, you need to be sure that your two equipment are physically close to each other. Okay, I've seen people trying to do an allocation with 20 kilometers between each of them. No way you will be able to do it properly. Okay, the idea is you will have a pressure and temperature which are quite similar, and it will be easier to see if one is deviating from the other one. You need to do the recording at the same time. I have seen, cases where they say, well, Bruno, we are recording this data today with a separator, and tomorrow, we will have the same thing with a multi-phase flow meter. No, I don't know what will happen between one day and the other. It's a recording at the same time. You need also to have the same PVT package. I have seen the cases where I have a separator with one PVT package. I have a multi-phase flow meter with another PVT package, and I was told to do a comparison at standard condition. obviously, you know, if you don't have the same PVT package, you are introducing some error, you know, and then you may conclude at the end that they are not matching. The two data are not matching, but I don't know which one is right. So some people will say, oh yeah, but I've been using this meter for so long that I know that this one is right. No, there is no way to state that. Okay, and please be sure that there is no choke between the two equipment. I have seen equipment close to each other, but they were a choke because the separator could not handle the pressure on a multi-phase flow meter. Unfortunately, there is a choke. There is a large change in pressure and temperature, but there is also a different flow structure. The structure of the flow will be different, you know, and therefore the response of the meter may be not right. And finally, let's be sure that the two equipment are in a sweet spot. You know, you are not working outside of the range of a separator. For example, you have a teeny separator, large production, you will have obviously carry over or carry under, you know, and in this case, you will not be able to establish properly the performance. Now that we have these things in mind, to be able to state that we can start a comparison, we need to be sure that we have a level of stability in the flow, okay, for a given choke, for example, or a gas lift condition. And all the idea here is to find something which is generic, okay, which is not specific to a multi-phase flow meter, you know, but generic to some basic measurements that you are doing in the field. And what we use, it's a pressure sensor, temperature sensor, and the differential pressure. I said earlier, you know, most of these manufacturers are using a Venturi, and if they are not using a Venturi, we can have a Delta P installed somewhere. And all the idea, we will be looking the noise, if you want, the noise from the flow, okay, on a short period of time, you know, we select 10 or 60 seconds. We need something, you know, which is not too long, okay? So we will have the root mean square of this pressure, and we will look at it against a pressure, an average of the pressure that we take on a longer period, you know, and this could be 10 minutes, could be 20 minutes if you want. The idea is to look at the noise that you have, or the fluctuation that you have in your flow here, against a very stable value. And you need to establish a criteria. This is a criteria that we are establishing ourselves, 5% on the pressure, 5% on the temperature is the same technique, and we establish 10% on the differential pressure. You can tie these things, this can be negotiated earlier. So these are the three things that we do, and we had another one which is associated with a square root or square root error, you know, of the differential pressure. It is a bit long to explain here, but the idea is the dP is associated with a mass flow rate, but there is a square root somewhere, you know, and you want to see if the average of the square root or the square root of the average are fundamentally different. They should not be, unless it means that the fluctuations are quite high inside your flow. So these are the four criteria and nothing else, and you can see it's very simple. Nothing is associated with the technology, no electromagnetics, no nuclear, nothing like that. It's purely what you have in your well. Okay. Things again that I want to say when you do a comparison, don't start to do a comparison of a multi-phase flow meter with an equipment where you are only taking some samples. Okay. This is quite amazing. I have seen, and I am presenting a real case here, you know, where we have a time and samples were taken, you can imagine from a separator, you know, and you have these 7 points here. And what do? You know, you have 6 which seems okay, you know, and you have 1 which you may remove, you know, if you want, because you say it's a bit too high, or if you take into account all of them, you know, you get this water cut now not at 34%, but 36%. And if you look at what was happening, you know, with a recording, you know, a continuous recording, and I show you that here, you can see that it was neither 34 nor 36, it was 42%, you know, and it was, obviously, you can see 6 to 8% difference, and this is what you will have on your oil flow rate and water flow rate. So please be sure when you do a verification in a field, all the equipment nowadays have a digital opportunity, and you should be able to use such concept. Okay. Keep in mind also that some of the parameters that we are using are a ratio. Okay, and the product of an average is not an average of a product. Very often I see people calculating an average WLR by doing the average of each WLR. No, this is not the way to do it. The way is to come back to the definition, and the WLR is the sum of the volume of water divided by the sum of liquid, or the flow rate if you want in your case, and this is how you do it. And also keep in mind, a water-liquid ratio is not what sometimes I see water cut or BS&W at standard conditions. They are not the same thing. If you look at here, you can see it's the water at line condition, here the water at standard condition, and the same thing in the bottom. So there is, as you know, some shrinkage happening. You have some gas at line condition that will come out. So the oil flow rate that you have here at line condition is larger than the oil flow rate you have at standard condition. So there is no way to look at BS&W from samples, for example, against a WLR from a multi-phase flow meter. These are the basic things that you need to avoid. Okay. So the goal of the test now, I hope you understand it, we will need to have some repeatability, some reproducibility. We need to look at in a lower range of the expectation of this well or this field, in a large range also to be sure that it works, and obviously something in the middle. Okay. So we are here now. We have this meter. We have done all this collection of data. We know that there is an uncertainty now associated with the multi-phase flow meter, but there is one which is also associated with the reference meter. Is it another multi-phase flow meter? Is it a separator? They have an uncertainty, and the uncertainty of both of them is comparable here. So you are not in a previous case in the beginning of my presentation where you had a high quality on the flow loop, and therefore you can disregard the uncertainty coming from the reference meter. Here you need to have a system in place capable to take into account the uncertainty of both equipment in order to say if the values that you are getting are comparable or not. And the first thing that I say on the top, before to show you the equation, is probably the most important thing here is to have a third party involved, because obviously you have the buyer on one side, the end user, you have the seller, the manufacturer on the other side, and you will have the third party, maybe with a separator on another meter, and then it will start to be a fight everywhere. So get someone in the middle that has the competency to handle this situation in terms of knowledge. Okay. So we know how to calculate the repeatability and the reproducibility, and now, and it's almost the end of my presentation, you will calculate what we call a zeta factor. Then the zeta factor will be the reading, the average that you will have for one given point from the multi-phase flow meter against the so-called reference, could be a separator, could be another multi-phase flow meter. But what is important, you don't look at the difference, you look at the difference divided by the uncertainty that you have on your multi-phase flow meter and the uncertainty that you have on your flow meter or reference measurement, plus the repeatability and the reproducibility of each of them. And this will give you a number. This number will go from 0 to 10 to whatever, there is no limit. Probably there is a crap between these two values here. Often you will be between 0 and 5 probably, and I'm giving you here how it's working, So if you have a zeta factor of 0, it means these two values are in average are perfect, so it's excellent. If it's below 1, it's excellent, and if you reach the value 2, it's still passing. So this value here, the ratio of both, is giving you 2. It's okay. When it's between 2 and 3, it's doubtful. You need to look at a bit what's happening, and definitely we know when it's above 3, you fail. So the comparison between both is not correct. The system doesn't tell you that this one is right and this one is wrong. It's just telling you that both systems, or the system make with these two measures, provide inconsistent value. Okay, and both may be failing, or one may be failing, and we don't know yet at this stage which one is failing. So you need to record more data in order to be sure to spot which one could be failing. Could be also because you are in a bottom of the working envelope of one of these measures, and therefore the uncertainty is much higher, and you didn't take very well these things into account. Obviously, when you look at this zeta factor is a continuum value. You know, it's not 0 or 1, and you cannot use the binomial law here like I presented earlier. So you need to have a statement in terms of success, and this is where you can play a bit around that. The way we do it in our case, it's we define the zeta factor as 2, and are you above 2 or below 2? Okay, and this, now we're back to what I was saying earlier. We have you are in or you are out. You have an uncertainty associated with that, which should be 95%, you know, and then you can reuse your binomial law as presented earlier. And you will be able to say you pass or you verify that the meter in the field is working against what you believe is your best reference. Okay, and it could be a separator well controlled, you know, well refurbished, you know, with a proper equipment, Coriolis, a water cut meter in line, you know, and things like that. Okay? Or, as I said, another multi-phase flow meter. So I'm reaching the conclusion here, and I have 3 slides for the conclusion. One associated with the manufacturer. We have seen it earlier. Most of the manufacturers today are not providing the relevant answer product for the end user, which means the uncertainty associated with oil, water, and gas. They provide something else, and they need to be careful because with the ISO and API coming, you know, they will be forcing, you know, to work a bit more in this direction and look at the sensitivity parameter associated with this number. There is also repeatability and reproducibility uncertainty that needs to be stated, okay? And it's coming more and more the fact that you need to establish the sensitivity to some parameter, salinity, for example, for electromagnetic measurement, or for some nuclear system, you know, or chemical and things like that. To be able to establish and evaluate the performance of a meter, you will need the repeatability, the reproducibility, the drift, the resolution, and obviously the uncertainty that you have during your test. This is what is important, and you will need to use the T distribution and not the Z distribution to establish a proper specification. And there is a way to analyze the outlier, and you don't remove an outlier because you don't like it. There is a statistic system to be used, you know. And obviously, to give some value to your test, you know, you should have this report, you know, coming from a third-party facility, and definitely not from a manufacturer flow loop or an oil company flow loop or things like that. It needs to be done in a way that it's fair and equitable for both parties, the end user and the manufacturer. Okay. If I look at it now from the end user and to check if the meter is working, you know, it's a concept of a criteria of pass or fail that I described earlier. Obviously, you need to establish this pass and fail criteria based on oil flow rate, water flow rate, and gas flow rate, and you use the binomial law, as I said earlier. Okay, and definitely, if you are expecting as the end user to see the salinity changing in your well in the future, you should do some tests, you know, to verify how the meter will be deviating here. Okay. And again, if for a reason, you know, the meter is not passing, you know, it's better that you have a report which is stamped again here by a third-party facility. Okay? In a field, when you are doing a comparison, verification in a field, you know, you need to use a zeta factor here because the two meters have a large uncertainty associated with each of them. When I say large, it could be 2% for each of them, at the opposite of what you will have in a laboratory with 2% on a multi-phase flow meter and 0.2, for example, on the reference, you know, so which is a factor 10 in this case. In the field, they are comparable, same order of magnitude, you know. You need to do some repeatability and reproducibility. I told you this is very important, and this is what you are using very often in the field if you are in a well allocation or partner in a field between different companies. Sensitivity needs to be established in a field also, you know. If you have some chemicals, you need to look at, for a given flow rate, you know, you don't change anything except changing the chemical, and then you can see how the meter is deviating or not versus this injection of chemical. Okay? Keep in mind, recording should be always done at the same time, same place, same condition, and obviously without a choke, as I said, between both systems. I should have highlighted this part here, but definitely I say it, you know, you need to be sure that you use someone, which is expert in flow measurement, and I will say, also in the uncertainty measurement, statistic measurement, in order to establish a report, that can be distributed to both of them. Obviously, this person needs to audit what's happening in the field, and to state clearly, yes, he passed, or unfortunately, he failed. Okay. So we are arriving at the end. Just before a few questions, I will take, as I said, in this 1 hour, I try to summarize a lot of things. One thing which is important, it's, I've been talking about this part here, there's a lot of things that I've been hiding, for example, fluid behavior and conversion from line to standard conditions. There's all these things to be done and calculated. Obviously, we are capable to do that. I try to simplify it and keep it at line condition, as stated earlier. So I have a good news now. It's a bit a sales speech in one way that I'm doing right now. We have this North Sea flow measurement workshop happening, end of October. I put North Sea between brackets, because obviously today it's wonderful with this digital world where we are, we have papers presented from Thailand to Brazil, so mentioning North Sea, it's probably will have been better to say the virtual international flow measurement workshop, but this, 38 years that we are 37 years, and this will be the 38 years, we're doing this event is used like that. I strongly advise you to copy this line here, for the web. Because what you can read now, it's kindly Nell will be proposing a discount, for all the people that have been assisting up to this slide 45, of this webinar. So if you send an email to me or to Marietta or the people that have been taking care about the registration, the booking for you for this webinar, we will be able to give you a specific code, and then you will have a discount for this North Sea flow measurement workshop. I give you here an idea of what we are going to talk over the 4 days. One is obviously associated with flow measurement from a user point of view, and the future, what do they see, what are the challenges. The day number 2, it's much more around the innovation with the flow measurement. What are the new things on the market? How do they use, for example, Coriolis in 3 phases? What are the new way to handle the data? A bit of data analytics, if you want, at this point. The day number 3, it's a day where I'm very excited because we are starting to have in this conference not only oil and gas, but also things associated with hydrogen, with flaring, with CO2, including CCS, carbon capture storage. So it's a very interesting day, the number 3. And obviously, when we arrive on the day number 4, we so digitalization, condition-based monitoring, and all these things. So there is a lot of things happening during these 4 days, and it could be interesting for some of you to assist at that. There is, even if it's a virtual event, there is also an exhibition hall. There is also some chat room, and this will be open for 30 days after the conference. So you will be able to exchange with the 200 or whatever the number of person right now. I think 250 I have seen when I went to the website the last time, so, and it will grow, I'm sure, before the end. Before continuing, I will ask Marietta if I can answer. I have seen some questions coming, so I may be able to answer a few questions if you are okay, Marietta.
Yeah, I'm just conscious of the time. I don't know if you want to maybe take 1 or 2 questions and then we will close the event.
Okay.
Are there any there that you want to pick up?
I like to talk, Marietta.
I know.
Okay, I will take the 2 first questions that I've seen. The first one is a very simple one. It's is a service, and I suppose the person is talking about the In-Situ Verification, is a service is provided by Nell, And yes, we are doing these things today. We are doing it for multiple reasons. And just to simplify it, I will say Nel over the last years has been recruiting few employees from the oil services company. So we have people who know exactly the challenge that you have offshore or subsea or land, and we have a large expertise, obviously, as you may know, in Nel, and we have been combining these two expertise, in order to be able to provide such services that I'm presenting in a way inside this presentation. The second question I will take, it's totally different here. It's related more on the T distribution, and the question is, did you see some oil companies, using such system with a T distribution to evaluate the performance of the multi-phase flow meter and the facility? And yes, it's quite amazing because I have seen a report given to us, in order to establish not with a K factor, like it may have been produced, initially because the manufacturer was asking us to put it with a K factor, but say, please, can you make it the right way, not with a Z distribution, but a T or normal distribution, but with a T distribution, and we are capable to do that, and we are very pleased to do that. It gives much more credibility to the work that we are doing.